We have discussed the basics of what a significance test is. What we're going to do in the next two videos is we're going to look at how we can test claims about a population proportion. So in the first part of this section, we're going to check the conditions for carrying out a test, and then we're going to construct a significance test about a population proportion. We're going to be looking at, in this video, how to do a one-sided test. In the second video, we'll look at a two-sided test. So here's a summary of what we've done so far in 9.1, the previous videos. We looked at the reasoning behind significance tests. We looked at what a p-value was. And we're going to look at the details included in testing claims about our population's proportions. In the next section, we'll look at population means, just like we have in the previous chapters. So again, in this video, we'll look at one-sided tests. In the next one, we'll look at two-sided tests and look at how confidence intervals and two-sided tests are kind of related to each other. So back to our basketball player who claims he's an 80% free throw shooter. We conducted a simulation in the previous section, and we had a sample proportion of 32 out of 50. That's 0.64, and that's lower than he claims. But the question is, does this provide convincing evidence against his claim? Or could it have randomly happened by chance? So we're going to perform a significance test with a null hypothesis of p equaling 0.8, an alternative hypothesis of p less than 0.8. P is standing for the actual proportion of free throws that a shooter makes in the long run. And this definition of what the parameter is something you should include. So there are conditions. We can't just do this whenever we feel like. Certain things must be met. And they're the same ones that we saw in the previous chapter. When we're dealing with an unknown population proportion, we can only construct a confidence interval and likewise only perform a significance test if the data was collected randomly, if the normal approximation is appropriate, and if the trials were independent. So in this particular experiment, these 50 shots could be considered random. They're a random sampling from every shot that this basketball player takes. Normal, we check NP and N1 minus P. N times P is 40, and 1 minus P is 10. Both of those are at least 10, so our normal condition is met. And in this case, in our simulation, the outcome of each shot is determined by a random number generator, so our observations are independent. Our three conditions are met. We can proceed. So if the null is true, then the player's sample proportions would vary according to an approximately normal sampling distribution. If this is true, we have an approximately normal sampling distribution with mu sub p, the mean of the sampling distribution, is 0.8, and a standard deviation calculated as such. So it looks like this. We have a normal distribution, or roughly normal. Mean, middle, is 0.8. We have our standard deviation of 0.0566, and we've shown the sample statistic p hat of 0.64 on this number line also. A significance test will use the sample data to measure the strength of the evidence against the null. Here are some principles. The first is the test compares a statistic calculated from our sample data with the value of the parameter stated in the null hypothesis. So we're calculating our p hat with what we're claiming to be p. Values of the statistic that are far from the null parameter in the direction specified by the alternative hypothesis give evidence against the null. So let's look at this again. Values of the statistic far from the null parameter in the direction specified by the alternative hypothesis. So we're looking to show that our mean is less than 0.8. So values of our statistic that are in that direction that are less than can give evidence against the null hypothesis. Sample values up here, that really doesn't matter. That's not what we're trying to show. Now, a test statistic, this should look familiar, but it measures how far a sample statistic is from what we would expect if the null hypothesis were true. In other words, how far is p hat from p in terms of standard deviation. This is a z-score, guys. This formula should look familiar. We just use slightly different terms when we're talking about a significance test. So, standardizing our test statistic of 0.64, we do 0.64 minus 0.8, divide by the standard deviation that we had, and we get negative 2.83. Using table A or using our graphing calculator, we can calculate that our p-value, our probability that we get values below 0.64 or z-scores below negative 2.83 is 0.0023. And if the null hypothesis is true, and the player does make 80% of his free throws in the long run, there's only about a 2 in 1,000 chance that our player would make as few as 32 out of 50 shots. And we probably should be rejecting the null hypothesis here. But let's formalize this a little bit more. We're going to take this to our familiar 4-step process. First thing we should do is state what hypotheses we want to test. We should be writing down the null hypothesis, the alternative hypothesis. We should be defining our parameters that we're using. We should also state the significance level, the alpha, that we're going to be concerned with. To plan, we're going to choose an appropriate inference method. In this section, it's all going to be checking for the proportion, a one-value z-test. We're going to check our conditions. Those conditions, remember, are SRS, independent, and normal. If those conditions are met, we are going to go on to the do part. We're going to compute the test statistic. We're going to find the p-value. And when we conclude, we're going to interpret the results of our test in the context of the problem. And that's sometimes the hardest part, in the context of the problem. When these conditions are met, the sampling distribution of p hat is approximately normal with a mean p hat of p and a standard deviation found by our good friend, the standard deviation formula that we've been using for a few chapters now. When performing a significance test, we're going to use slightly different notation. The null hypothesis specifies a value for p. Remember, we don't actually know p. We're making a claim that p is something. So the correct notation we should use would be p sub 0, p naught, in place of these p's right here. We're assuming that this value is correct when performing our calculations. So again, our one sample z-test for a proportion, we're choosing an SRS of size n from a large population that contains an unknown proportion of p successes. To test our hypothesis, our null hypothesis, compute the z statistic, the test statistic. And we find the p-value by calculating the probability of getting a z statistic this large or larger in the direction specified by the alternate hypothesis. And these are the pictures that we'll end up. We're going to look at and focus on one of these two in the next example. In the second video, we will look at a two-tail situation. But remember, we can only use this if we meet the normal condition and the test for independence. Test for independence, remember, is the 10% condition, and the normal condition is NP and N1 minus P. And in this case, we're using N times P naught, N times 1 minus P naught. This is the claimed value for our proportion. So, example time, and then we are done. We're going back to our potato chips. Our potato chip producer just received a truckload of potatoes. We want to determine if more than 8% of the potatoes in the shipment have blemishes. Because if they do, we're sending the truck away and we're getting a new load. A supervisor selects a random sample of 500 potatoes. An inspection reveals that 47 have blemishes. Carry out a significance test at alpha equals 0.1 significance level and figure out what we should conclude. So, we're stating our null and alternative hypothesis. We're stating our alpha. We're also defining what P means. That's how you should start every single one of these tests. Now, to plan. Planning is checking our 3 conditions. We took a random sample. Assuming that P does equal 0.08, that 0.08 is our P naught. We're going to do n times P naught, we get 40. N times 1 minus P naught, we get 460. Those are both at least 10. We're good to use the normal calculations. And independent, we're sampling without replacement. We need to check the 10% condition. And it seems reasonable that there are a lot of potatoes in this truck. Probably at least 5,000 potatoes in this shipment. So here we go. Our P hat from our sample is 0.094. That's slightly bigger than 0.08. But is it too big? That's what we're testing. We calculate our test statistic. We get 1.15. We use our normal calculation, our table A. We find that the probability of being bigger than 1.15 is 0.1251. And since this p-value is greater than the significance level of 0.1, we fail to reject the null hypothesis. Our rejection region would be out here. We're not far enough away from the mean. So what would happen here? There is not sufficient evidence to conclude that the shipment contains more than 8% blemished potatoes. The producer should use this truckload of potatoes to make potato chips. I hope that you're seeing there's a lot of similarity between what we're doing here for our tests and the things that we did with our confidence intervals. Our conclusions and our do parts are slightly different, but a lot of the same skills are being used over and over and over. And this, ladies and gentlemen, is where we shall stop for today. The next video will look at what happens with a two-tailed test.